Okay, so Brandy, since you're in here now, just to recap really quickly, what you guys are working on this week is reviewing for topic 2. So that covers both the SL and the new HL stuff that we did last week. Because next week on Tuesday, you're going to do your test on topic 2, both the SL and HL level material. And also next Tuesday, we will not be having a Zoom call because of the PSAT test and the fact that teachers are helping out with that, and only the testers will be on campus. Everybody else, you'll be staying home and doing virtual, so you only have to log on to Canvas to do work that day, no Zoom calls. So I was just telling them that this basically starts out with a lot of the SL material review first. So your basic stuff like proton, neutron, electron, where are they located, what's their mass, what's their charge, mass number, atomic number, isotope, how do we write the symbols for the isotopes with their protons, neutrons, electrons, and how do we calculate them. And then I was kind of talking in here about how to calculate average atomic mass, because this is not something we really reviewed last week from the SL level. And so it depends on how the information is presented to you. If you're given isotope symbols, like this one on number 9, then you have to remember that this number up here is the mass number. So that's the number that you use for the mass. And then you multiply it by the percentage. You just need to make sure to change the, so you want to change it to decimal form. So for example, on this one, I would do 0.76 times 63. And then I would add 0.24 times 65. So make sure you put those in parentheses and do the multiplication first and then add those two together. Now, if they give you a graph like this one down here, this is what I was talking about when you got on the call. It's the same information, it's just presented slightly differently. Down here on the x-axis are your masses. So this one's got this isotope has a mass of 24, and then the percent abundance is on the y-axis. So this 78.6 is the percent abundance. And so on this one, I would do like 0.786 times 24. And then I would do the same thing for any other isotope. So this graph shows me that there are 3 isotopes for magnesium. Okay. So depending on, if they give you the symbols and the percentages, or if they give you the graph like here on the right, you might have to get the data slightly different, but the process to calculate it is the same way. Okay. The other thing is like here on number 10, this one is like the tricky one, because they give us the relative atomic mass, they give us the average, and they tell us here are our 2 isotopes. One has a mass of 11, one has a mass of 10. They want us to calculate the percent abundance of each isotope. Okay. And so, or actually it just wants the percent abundance of the boron 11. Okay. But what you have to do there is you have to kind of pretend that we know percentages are out of 100. So we know that both of those have to add up to 100%. And so we're going to pretend, instead of doing 100, because that's a harder number to deal with, we're going to make sure we're going to pretend it's 1. And so what you would do is I would say, just like I set up this one and I did mass times the percent times the mass, I would say, okay, well, the one of them, I'm going to call maybe the one that's 10, I'm going to call its percent X. And so I would do X times 10 plus, and then the other one, I would have to do 1 minus X times 11. And the reason I can do that is because I know that because I'm talking about a percent or a natural abundance, I know that both of these isotopes, they have to add up to 100%. And in decimal form, that means they have to add up to 1. So if I pretend one of them is X, then the other one, its percent or its amount has to be 1 minus X. And so by doing that, then it's just algebra. It's distributing your numbers, okay? And then combining like terms, and you want to solve for X. And so all of this is going to equal the average. So this will equal that 10.80. And then you just distribute your numbers, combine your X's and combine your like terms, and then get X on one side and get the number on the other. And then that'll give you X. And X is the amount for the isotope with 10. They want the isotope of 11. So then you would have to do 1 minus that. And then after you subtract, since they want the percent abundance, then just multiply it by 100 to make it a percent form. So move the decimal 2 places to the right. That's the opposite of what we do here when we move them to the left in order to do the calculation normally. All right. Now it's going into the second part of the SL where we kind of started talking about light, electromagnetic spectrum. So like frequency, energy, and wavelength, how are those related? How are my different types of light? How are they arranged by, increasing or decreasing on one of the properties, frequency, wavelength, or energy? Continuous and line spectrum, what do they look like? What do they mean? What do they tell us? How do they, all the information? And then if you have these electron transitions, are they going to give you, for hydrogen, are they going to be in the visible spectrum, infrared, or UV? Okay. And that's based on what we talked about when we reviewed last week as well. Excuse me. 22 and 23 get into the HL type stuff. So you're converting wavelengths to frequency. So on 22, pay attention because they give me nanometers and micrometers. So I need to convert both of those to meters. And then once I have the meters, then I can use the speed of light equation, that C equals wavelength times frequency. I can use that to rearrange and get frequency is C divided by wavelength. The only thing is the wavelength has to be converted to meters first before I can plug it into that equation, okay? 23, you're basically doing that calculation. You're doing several other calculations. So depending on what they give you. So like number 1, they give us the frequency. So you can use this equation, rearrange it to solve for the wavelength. And that's how you would fill in the second column. To get energy, I'm going to use my other equation. That's the energy is Planck's constant times the frequency. That's how I can get the third column, okay? So depending on what they give you, you're going to use one of these two equations and just manipulate it around until you're solving for the one that you need, okay? I will say, though, be careful, though, because like on number 2, the wavelength is in meters, but on number 3, it's not. So you're going to have to convert that to meters first before you do that calculation, okay? Questions about electromagnetic spectrum. So it says each of the lines in 23, and so it says which region. So basically what you can do is once you know the energy over here, you should be able to kind of match up the energy or the wavelength, either one. You should be able to match these numbers up to an electromagnetic spectrum and sort of estimate where they would fall. Are they in the visible light? Are they in infrared? Are they gamma ray? Okay, that kind of stuff. And it says you can use the data booklet because there is an electromagnetic spectrum in the data booklet. I can't remember which page it's on, but it's in there, okay? Convergence limit, that's what we talked about with the ionization energy, first ionization energy calculations. The equation for an ionization, that's directly from stuff we talked about last week with HL. 27, this is where you're doing what we did like last week. So you're going to do the light calculations like on 23, but then you're going to multiply it by Avogadro's number to get per mole. So it says, calculate the ionization energy of hydrogen in kilojoules per mole. And it says the frequency of the convergence limit for the series of lines where the electron returns to the ground state is this. So they're giving us this frequency, okay? So they're not even giving us wavelength. We don't even have to use the speed of light equation. They're giving us frequency. So I just need to use this equation to calculate the energy. And then once I have that energy, because they want it per mole, I need to multiply by Avogadro's number. And then I would also need to convert it from joules to kilojoules, because when I do this equation, energy comes out in joules. So you will have to divide by 1,000 to make it kilojoules, just like we did last week on the practice. Now, this one, it goes back to some of the SL stuff with electron configuration. So it's going to talk about orbitals like SPDF, the subshells, the energy levels, all that kind of stuff, writing electron configurations, the short ones and the long ones, drawing the orbital diagrams with the up and down arrows. And then the last little part goes back to talking about what we talked about last week with the ionization energies, and looking at these graphs in order to determine sort of what group the element's in based on this graph, because we talked about when there's a bigger jump, that's where it's lost the last valence electron and it's gone to the next energy level down. And then same thing here, it's just instead of a graph, it's giving you a table of values. So again, what you want to look for is where's the largest jump from one ionization energy to another, okay? And then at the end, it goes back to just a few more electron configuration questions here, like on 44. So it kind of covers a little bit of everything SL and HL on topic 2/12. And so you guys are going to have today and also Friday to work on that. So if you work on it some today and then you run into some problems, and when we get on the call Friday, we can kind of look at those questions and see where you're having trouble and go over them before you guys do your test next Tuesday.